Hello everyone, I'm Daniel Treffer, the founder of MeltPrep. We are a lab equipment producer based in Austria. It's a great pleasure for us to participate in the Antec 2021 and I hope you're all having a great time at the conference. I will talk about my invention, vacuum compression molding. I invented the process to prepare samples for investigations on polymer melts used for pharmaceutical purposes. Let me start with a short story. Imagine we work on new materials and want to characterize them. We may need some solid bodies to determine the material properties precisely. When I had to do it for the first time, my immediate reaction was, how difficult can it be? But the requirements are high. We want our samples to be perfect, homogeneous, without air inclusion, without moisture inclusion, and a defined shape. After failing for quite some time, my perspective on the problem changed. In addition, I was struggling with material costs. Materials are expensive during early stages in R&D. Gold with about $57 per gram is almost a bargain in comparison. So you can imagine I had a lot of question marks on my mind. And as it turned out, I had to invent something new to clear them out and get access to the desired material properties. This here is my invention, the VCM technology. With vacuum compression molding, one can prepare these flawless samples with ease. It is the fastest way from powder to sample, and this is how it looks on a lab bench. The platform I have designed to make the VCM process easy to use is called VCM Essentials. On the left hand side is the heating unit, the vacuum unit is in the back, and the cooling unit is on the right hand side. The VCM tools are manually placed on the heating unit or cooling unit as they go through the processing steps. Let me show you an illustrative video of how it works. This is the heart of the VCM technology. A PTFE foil is rolled up to cover the lateral surface of the VCM chamber. A disc-shaped foil covers the bottom of the VCM chamber. It is lightweight and can be filled on an analytical scale directly. After filling, the opening is covered with another disc-shaped foil on top. The foil's arrangement allows the piston to go up and down. The volume of the chamber is adaptable and allows the piston to follow the material behavior during processing. After the VCM tool is connected to the vacuum unit, the air is drawn out and the powder is compacted. Subsequently, the VCM tool is placed on the hot plate to initiate the melting. The powdery material forms a homogeneous melt. As a rule of thumb, this takes about 5 minutes. Once completed, the VCM tool is transferred to the cooling unit to cool it down to ambient conditions. After cooling, it is taken apart and the sample can be released with ease. The PTFE foils can be peeled off like stickers. Here you can see the entire VCM Essentials again. A typical sample preparation takes less than 10 minutes. Heating is performed in some minutes and can go up to 300 degrees Celsius, making it suitable for most R&D applications. Cooling generally also takes only some minutes. At the end of the operation, there is no tedious cleaning required, making the process time efficient and lossless. Most of you probably know multiple methods to prepare samples. We compared their performance. In conventional preparation approaches like injection molding, viscous dissipation and strong extensional flows can cause thermal or mechanical degradation. Air voids or possible moisture inclusions often remain within the sample, harming subsequent experiments or measurements. Or you may even face another difficulty. Have you ever tried to die cut an amorphous, brittle material? It will just scatter and leave you with 1,000 pieces. VCM fulfills all the requirements listed in this table, with the massive plus of saving high quantities of material, producing homogeneous samples without moisture and air inclusions, thanks to its entirely evacuated processing steps. VCM is designed in a modular manner. Interchangeable inserts allow you to prepare different disk dimensions with one VCM main body. With a different body, the VCM bar tool, you can prepare also elongated samples like rectangles. We can also tailor any two-dimensional shape. Even more complex shapes like tensile bars are possible on customer request. Since the VCM principle is lossless, you can easily define the height of your sample yourself. The material's solid density is the factor between the height and the filled mass. You can easily calculate the height of your sample with the formula below, or you can use our height calculator that also has a database for a common material by clicking on our web page or scan the QR code on this slide. The entire portfolio of dimensions that you can produce with our VCM tools is shown here. You can make disc-shaped samples with a diameter between 25 mm and 0.3 millimeters, or you can do bars with the VCM bar tool, allowing you to have rectangular bars of 10 by 40 or 5 by 20 millimeter, or standard small scale tensile bars for the characterization of mechanical properties. One thing that I'm very proud of is the small scale development that we did. I kicked the VCM tool off with a 25 mm disc diameter in 2014. My former colleagues at the RCPE were requesting smaller dimensions for their investigations. We reduced it to 5 mm to make it suitable for DSC and later even to 2 mm diameter. You can use those small dimensions for the screening of implants, for example. 1 to 50 milligrams are sufficient to produce a prototype of a subcutaneous implant. This is a game changer. But we did not stop here. We recognized the need for even smaller tools with even lower material requirements. Let's imagine samples with a length to diameter ratio of 1 and a 1 gram per cubic centimeter density as an educated guess for a polymer density. When we look at the 2 mm sample, we would only need 6 milligrams. For a 1 mm sample, it's already less than 3 milligrams. For 0.8 millimeter, less than a milligram. If this is still too much material for you, or if you're just interested in designing very small things like an intraocular implant, you can use our smallest dimension with 0.3 or 0.5 millimeter, bringing you in the sub-milligram range. Do you like these flawless samples here on this rotating video? Each of them was produced in less than 10 minutes. Let me show you some of our leading applications. It all started with sample preparation for rheology during my PhD, but my colleagues were interested in other analytics as well. So DMTA, solubility testing, hardness testing, color testing, and much more were explored quickly. It soon turned out that our customers are much more creative in using our tools than we are. To understand the benefit of VCM, I think it's essential to talk about how an API is mixed into the carrier material, or how different polymers are blended together. Unlike an extruder, VCM does not mix mechanically. With vacuum compression molding, you only compress and melt the material. To illustrate the mixing mechanisms, we have prepared the following examples. If one puts multicolor pellets into the sample chamber and runs the VCM process, one will obtain a disc without any air inclusions. But you can see the phase boundaries between the individual particles. There are no shear forces and there is no macroscopic mixing. How can we obtain a homogeneous result then? Let's recall the mass transfer basics that we have learned in school. There are two mechanisms. First, convection, also known as shear or mechanical mixing, and second, there is diffusion. We do not have significant shear forces, only very negligible convection. So we need to empower the second thing. We need to empower diffusion. This can be done by using powders with a smaller length scale instead of pellets, enabling very powerful mixing via diffusion. We used an orange color dye on HPMCES powder as a powder blend to illustrate that. As a result, a good fraction of the color tracer already diffused inside the polymer disc. but there are still some agglomerates visible. That's why homogeneous powder mixtures as a starting material are so crucial for our process when homogeneous single-phase results are desired. To improve homogeneity, we have to empower diffusion by reducing the length scale further. The way how we usually recommend doing so is milling, preferably cryomilling. Reducing the particle size before processing via VCM will let you obtain an extrusion-like result. In the pharmaceutical world, often an amorphous transparent disc. Another option is solvent casting. We dissolve the mixture in a suitable solvent and let the solution evaporate. Take the remaining film off from the petri dish and put it into the VCM tool. It will also shape it in a completely homogeneous disc that is extrusion-like and suitable for further investigations. Considering the mixing, I can also answer one of the most frequent questions that I receive in the pharma arena. Are VCM samples comparable to Hotmelt extrusion? Hotmelt extrusion is the term used in pharma for compounding. Professor Repka's PhD student Gowrie conducted a very comprehensive study. In this case, the model API indomethacin was used to study if Hotmelt extrusion and VCM yielded similar results. This slide shows images of VCM samples with 8 mm in diameter with some common carrier materials including Bartek MXP. The samples went through intensive characterization showing comparable data to Hotmelt extrusion. I want to highlight the dissolution data. The VCM and extruded samples were both milled and then subjected to dissolution. One can see significant differences between the carriers, but you can also see an excellent agreement between VCM and HME. It proves VCM as a screening approach, giving extrusion-like properties and requiring only a small fraction, less than a gram of material per formulation. Their paper is open access and linked on the QR code on this slide if you want to read more about this. Let's move on to a more common analytical technique for a polymer audience, melt rheology. VCM can help you with product development tasks. Rheology on VCM samples can help to find processing window of your extruder. But during my PhD, I realized it can only help if you receive reproducible data. During viscosity measurements, shear is applied to a molten sample and the required force is recorded. A rheometer assumes a homogeneous sample. Inhomogeneities, like bubbles or even a degraded sample, simply lead to wrong data. Compare these two images just taken before the measurement. The perfect sample on the left and many bubbles in the powder sample on the right side, without proper sample preparation, of course. How can it be applied for extrusion developments? In general, the viscosity of a base material can be lowered using plasticizers. Most active pharmaceutical ingredients, short APIs, are small molecules and act as plasticizers. Adding 30% of API reduces the viscosity from a 3000 Pascal second level at 170 degrees C to only 5 Pascal seconds. 3 orders of magnitude. That's a lot. The time-temperature superposition allows you to shift those curves to different temperature levels. You can predict operating temperatures before you even start the extruder. In this case, it predicted the temperature decrease from 170 degrees C for the neat polymer to 100 degrees C for the polymer API mixture. And the best of it, it just worked perfectly when we turned on the extruder. Literally no process development was required. Temperature superposition with precise data is very powerful and can save quite some money when you work with pricey materials. Less material is wasted during the process development and you gain valuable know-how to reduce the operating temperatures to avoid degradation, for example. People usually ask me how much material is required for such a study. Will it save us any material at all? We have depicted the requirements here. Standard rheology tests are done 3 times for each API concentration. So 12 samples weigh around 12 gram with 1.8 gram of API loading. To reduce the amounts further, you can use microrheology. 12 samples with 8 millimeter diameter require 300 milligrams of material and only 45 milligrams of API. Imagine operating an extruder at the lowest throughput that you can find, let's say 20 grams per hour. You have less than a minute to find the operating parameters before you wasted more material than you would need for rheology. If this is still too much for you, even smaller sample sizes are available, but they are also require experienced rheologists to perform the measurements. 10 milligram of the material required equals to an extrusion time of a few seconds only. Is it worth spending a bit of effort in rheology? I think the possible savings with standard rheology are already enormous. Rheology can give you quite some insight when done with flawless samples, and certainly something that I highly recommend for material or process development. I also like the possibility of multi-layer samples with VCM. VCM allows you to fuse multiple layers to one specimen. So you can prepare various layers in advance, one by one, and load them into the VCM chamber, process them in another cycle into one single specimen. You obtain a multi-layer sample with distinct layers and sharp interfaces. For example, if you work with composites or you're interested in interlayer properties, for example, you only need 2 VCM samples out of different materials and some separation foils that have pressure-sensitive adhesives on one side. Place one foil on each sample, place them into the VCM tool. After one processing cycle, you fuse them in a defined area, in our case 1 by 1 centimeter, cut the parts with the foils and receive an excellent sample for a shear adhesion test, for example. One other application for multi-layer systems is out of the pharma world. I will talk about intravaginal rings used for birth control. A famous example is the NuVa ring. Engineers may think it looks like an O-ring, but it has a complex structure. It uses a drug-loaded core with a surrounded diffusion barrier to limit the drug release. A research group in Graz wanted to mimic the complex structure of the NuVa ring. The final VCM sample that they used was a sandwich of 2 100 micrometer thin diffusion barriers filled with a drug-loaded core. Then they covered the lateral surface with barrier glue, used optical coherence spectroscopy to check for interfaces and see if diffusion barriers are uniform in thickness. Afterward, they subjected the sample and the co-extruded version to dissolution. In the dissolution curves, you see a good match of VCM and the co-extruded samples. What does that mean? It's empowering the single researcher. One single scientist can perform the VCM process, making samples the first half of the day, and has still time in the afternoon to focus on research. Whereas with co-extrusion, one has to conduct quite some process development. I guess this audience here probably knows better than I do, but we are talking about weeks when material is new, with unknown properties, and also kilograms of material before a good prototype of a new formulation can be obtained. This is a huge advantage. Recent developments allow us also to manufacture core sheath structures in less than an hour. A 2 millimeter implant with a length of 10 millimeter is entirely embedded in the sheath. The fusion of pre-manufactured samples is the base for the sharp interfaces that you can see here. Let's move on to the next example. This study was performed by the University of Dortmund and Merck Darmstadt in Germany. The scientists investigated copovidone, a polymer commonly used in amorphous solid dispersions, to assess how the added API influenced its mechanical properties. In this work, a small VCM disc sample was used for several applications. AFM, texture analyzers, diameter compression tests, and surface tension measurements were performed. There are plenty of instruments on the market to study mechanical properties on small-scale samples. Indeed, very interesting work. Another exciting application is seen in this study conducted by a student of Professor Möller on the self-healing properties of polymers. A VCM disc sample was cut, resulting in the rupture and the deformation of the ionic clusters. Then the material was slightly heated again to observe the subsequent healing process. VCM enabled constant pressure on the sample without applying shear or squeezing the sample too much. This study allowed scientists to focus on the structural composition of the material and the properties of its constituents. Let's move on to a color measurement example. VCM is very valuable when it comes to the measurement of color of master batches. Here we've used blue multicolor pellets via injection molding, first on standard test samples with 15 by 15 centimeters and a thickness of 2 millimeters, and compared it to standard samples produced via VCM with 25 millimeter in diameter. The first significant difference we can see here is the amounts of material used in the sample production by injection molding is way higher compared to vacuum compression molding. The route via VCM is very attractive when you have very limited amounts of a retaining sample available, for example. Another point is the material uniformity in the sample. We do expect a high uniformity once the pellets are fused together. And the large sample itself seems with a uniform texture. But we have to consider that this is the case because thousands of pellets were mechanically mixed in a molten state. They were just like molten and then injected through the gate into the cavity. But if we take a closer look at the VCM sample, where we can maintain the pellet shape basically, as we saw in the mixing example on one of the previous slides. When we look at this sample closely, we see that the pellets are not uniform. They have different color. This is a problem when you want to produce color-sensitive products, or in particular when you desire small parts via microinjection molding, for example. The last application I would like to show you today is spectroscopy. We can mount two processing sensors into a dedicated VCM spectroscopy chamber, studying the perfect PAT method for your application. And the best of it, you don't need an extruder. Everything works benched up. You just mount the two processing sensors, fill the chamber with the material. It easily allows you to develop your chemometric model or choose a suitable spectroscopy method for your material. This also just requires some grams of material per run, significantly lowering the material requirements in contrast to running calibrations on extruders. You saw many completely different application possibilities enabled by our easy-to-use VCM technology. Like I mentioned earlier, you are always more creative in using it than we are, so I'm excited about what you are doing next. Finally, I would like to give you a short overview of the entire MeltPrep portfolio. You already know the VCM technology for the lossless preparation. The second innovation is called the V-chamber. The V-chamber turns a regular hot plate into a vacuum oven. Place your sample onto the hot plate and put the V-chamber over it. You can apply vacuum and melt or dry your sample directly under vacuum on your hot plate. You can even think of using it on your measurement instrument directly, on the rheometer, for example. And last but not least, Extravis, our residence time distribution instrument. A useful tool for scale-up and troubleshooting of continuous processes. It's a camera-based system allowing you investigations of residence time distribution, giving you insights into mixing and degradation. It can also help to trace down color uniformity problems. You apply a color tracer at the inlet and point the camera to the outlet. The supplied software uses the color response at the outlet to provide the RDT analysis for you. You get the residence time distribution fully evaluated by a click of a button. Then you can compare and trace down the problems that you might see in the process developer. That's all about our portfolio. I would be delighted to talk about your challenges and try to find ways how we can overcome them together. That's why I invite you to book a free video demo via our webpage. You can send in your material and we do the demo on your material. You can conveniently book it via our webpage, meltprep.com, or contact me via my contact details shown here. I want to thank my team for their help during the preparation of this presentation and the recording, and I would like to thank you for your attention. Thank you very much.